This is a presentation of recent work concerning the Weisfeiler-Leman algorithm on planar graphs. The setting of the presentation is the graph isomorphism problem. Given two graphs, the task is to decide whether there is an isomorphism, an edge-preserving bijection between the vertex sets. So we are looking for a way to map this graph onto this graph without breaking or adding edges. The problem clearly is an NP because you can guess the isomorphism and verify it efficiently, but no polynomial time algorithm has been found so far. The best known procedure to solve the problem is due to Babai and runs in quasi-polynomial time. His algorithm, as well as all competitive ones applied in practice, use a central combinatorial technique called the Weisfeiler-Leman algorithm, which is the focus of this talk. Suppose we are given two graphs, for example, of chemical molecules, where vertices are atoms and edges represent chemical bonds. We want to know if the graphs are isomorphic, if they represent the same molecule. In order to restrict the number of mappings that we have to consider as candidate isomorphisms, we can exploit colors, so knowledge about atom types. Oxygen must be mapped to oxygen, hydrogen must be mapped to hydrogen, so red must be mapped to red, black to black, white to white, and so on. However, in the general case, trying out all possibilities to map white to white will already take too long. So large color classes are a problem. But in fact, this is a different type of white than this one or this one, because the vertex here is adjacent to red and all other white vertices are not. So we can use colors and propagate them through the graph to compute new colors, this way excluding more candidate mappings. And in the given example, we can directly deduce that the graphs are not isomorphic, as such a red-white combination does not exist on the left-hand side. This is exactly what color refinement, also called the one-dimensional Weisfeiler-Leman algorithm, does. Roughly speaking, it takes an input graph, applies a local refinement criterion repeatedly to compute colors, and only stops when the color partition is stable. So all white vertices are actually the same type of white, informally speaking, and the same holds for all other colors. Due to its very efficient implementation, the algorithm is used in all competitive isomorphism solvers. Let's look at the refinement criterion in more detail. Two vertices obtain different colors if there is a color which appears a different number of times in their neighborhoods. Let's look at an example. On this input graph, we can apply the criterion to distinguish the end vertices from all other black ones because the end vertices only have a single black neighbor. So we assign to them the new color blue. And in the next iteration, we can use this information to distinguish this vertex and its counterpart on the left from all other black vertices because they are the only ones with a blue neighbor. We can iterate the process until we are in this situation. Now you can verify yourselves that no further vertices of equal color can be distinguished via this criterion. This colored graph is the output of the algorithm after n/2 iterations, where n is the length of the path. On a second path of equal length, the algorithm would compute the same colors. So, by contraposition, we can use the algorithm to detect non-isomorphism. If two graphs result in different colorings, they must be non-isomorphic. So if two graphs yield distinct outputs of the algorithm, if they are distinguished by the algorithm, then they are non-isomorphic. However, the converse is not true, as these two example graphs, this one and this one, show. In these graphs, all vertices look the same towards the algorithm because they have the same colors in their neighborhood. The algorithm immediately stops on this input and outputs the colorings that you can see there. We cannot use them to distinguish the non-isomorphic graphs because both of them just have 6 pink vertices. We encounter the same problem on all pairs of regular graphs of equal order and equal degree. The algorithm immediately stops. So in order to distinguish more graphs from each other, higher dimensional versions of the Weisfeiler-Leman algorithm have been introduced. For example, 2WL colors two tuples, so pairs of vertices, also with respect to some local refinement criterion. One can show that on paths, the algorithm 2WL terminates faster than 1WL, namely in a logarithmic number of iterations, but this is not true on all graphs. However, like for 1WL on regular graphs, there are also pairs of graphs on which 2WL terminates immediately. The concept can be generalized. For every natural number k, there exists a k-dimensional WL algorithm which colors k tuples of vertices iteration by iteration, applying a refinement criterion with respect to previously computed tuple colors. The algorithm runs in polynomial time, and it has links to many seemingly unrelated areas of theoretical and practical computer science. An equivalence that is very useful to prove statements, particularly about the higher dimensional versions, is given on this slide. So KWL colors two graphs G and H differently if and only if the counting logic fragment CK plus 1 distinguishes the graphs. And this counting logic fragment allows to use only k plus 1 variables but counting quantifiers, as you can see in this C2 example with variables x and y and counting quantifiers. And this again is equivalent to spoiler winning a certain Ehrenfeucht-Fraissé type of game on the two graphs. So the colors that WL computes correspond to formulas in the logic. We have colors and we have the logic formulas. The correspondence is particularly tight because the number of iterations that the algorithm needs to compute its final output equals the nesting depth of the distinguishing formula and also the number of rounds played in the game. In particular, a bound on the iteration number of KWL on G and H gives us a bound on the descriptive complexity of the difference between the two graphs. But how many iterations does it take for KWL to compute its output on a certain input graph? This table gives an overview. Last year at ICALP, I presented a tight lower bound on the iteration number of 1WL of graphs of order n. However, for larger k, only a good upper bound in the case k equals 2 is known, and there is still a gap between the lower and the upper bound, even more for k larger than 2. Note that this lower bound has not been improved for 20 years. So we have seen that studying the number of iterations is difficult, and instead of studying it for all graphs, we can restrict ourselves to interesting graph classes. Specifically, if one can prove a logarithmic upper bound on the number of iterations of KWL to distinguish two graphs from a certain class, then this shows that the isomorphism problem for the class is in the complexity class AC1, which means it can be decided by Boolean circuits with logarithmic depth and a polynomial number of unlimited fan-in and an OR gates. Our main result states that, in fact, on the class of planar graphs, we can identify the input graph in a logarithmic number of iterations with a constant dimension of the algorithm. So when we are guaranteed that at least one of the considered graphs is planar, then we can decide isomorphism between them in a logarithmic number of WL iterations. By the correspondence to logics that we have seen, this is equivalent to saying that for some constant k, every planar graph of order n is definable with a ck sentence of logarithmic quantifier depth. And we say every planar and vertex graph is definable in C O of 1, O of log n. So we write the number of variables in the exponent and the nesting depth in the index. In the remainder of the talk, I will outline the proof for these statements. A graph is called planar if it can be embedded into the plane without edge crossings. Examples for this are our two molecular graphs from the initial slides. One can easily imagine them as flat objects embedded in the slide. And once we know the embedding, we can then start reasoning about vertices lying in certain areas of the graph. For example, this vertex lying in this face of the graph, which allows us to use geometrical or topological arguments. However, we don't know the embedding because it is not unique, and we don't know, for example, if this vertex will lie in this face or outside. So we could also flip it outside and it would still be the same graph but a different embedding. So we need that the embedding is unique in a sense. And for this, we need the notion of three-connectedness in graphs. A graph with at least 4 vertices is called three-connected if eliminating less than 3 vertices never splits the graph up into various components. One example is this complete graph on 4 vertices that you can see here together with a plane embedding. Whitney's famous theorem about 3 connected planar graphs yields that all of them have combinatorially unique embeddings. And this is what we need to be able to reason about vertices incident with faces or certain regions in the graph. So this is a 3 connected graph, And in every embedding that we choose, these 3 pink vertices will form a face, and the black vertex will lie in the face, for example, in this embedding. And using this uniqueness of embeddings, Verbitsky proved that a constant number of variables suffices to distinguish any 2 non-isomorphic 3-connected planar graphs of order n with a sentence of quantifier depth logarithmic in n. So without this 3-connectedness, this is our main theorem in terms of logics. So Verbitsky actually proved our result for the 3-connected case. And for our generalization to all planar graphs, we will use his theorem as a base case. In our paper, we gave an alternative proof for Verbitsky's result, which provides us with the stronger version that we need, and I will sketch it in the following. Given a 3-connected planar graph, such as this one, we can, by Whitney's theorem, assume it is embedded just like here in the picture. So the embedding looks actually like this. We then apply a procedure that reduces the graph to a simpler structure, this one, with phase cycles whose length is bounded by a constant. So every length of such a cycle defining a phase is bounded by a constant. And we can do this in a logarithmic number of steps. And skipping details, this allows us then to have formulas that describe such angles in a phase, so such triples of vertices defining such an angle in a phase. And these angle formulas allow us to then fix 3 vertices, for example v1, v2, v3, such that we get one formula for every vertex w in the graph, which identifies w, so which holds if and only if the input vertex is w. So when we have w, the formula is satisfied, and when we have another vertex, it's not satisfied. The formula describes a particular path from v1, from the first vertex, to w, for example this one. And so if we start in v1 and follow the path described by the formula, we will end up in this particular unique vertex w. So the formula will be false for all other vertices. Speaking in Weisfeiler-Leman terms, since formulas correspond to colors, this means that every vertex in the graph will receive its own unique color after a logarithmic number of iterations. And this will be important for our base case. The fact that we have vertex formulas or unique vertex colors allows us to identify the graph, because we can simply define it by stating for every pair of vertex formulas whether the corresponding vertices are adjacent or not. So we can write a formula to state that, for example, let's say this would be blue. The blue vertex and the green vertex are adjacent or are not adjacent depending on whether they are neighbors in G. And we can proceed like this to define the entire edge relation on G. So this result gives us that 3 connected planar graphs are identified. But how can we cope with general planar graphs? A useful tool when the graph structure is too complex is to deal with parts of the graph separately. So we decompose the graph into certain components, these gray shapes that you can see here, and deal first with the components and then combine them to deduce results for the entire graph. Here is a picture of a decomposition of a graph, and if the decomposition, so the object formed by the gray shapes, has a tree structure, then we can start by identifying the leaf components and storing information about their isomorphism types in these cut vertices, the big ones here. So we store in this vertex that a graph of green type and a graph of yellow type are attached to it. So we can cut them off and ascend iteration-wise, level by level, up to the root until we are left with only one gray shape, which we can then deal with using the base case. So in order for this approach to be useful for us to show that a logarithmic number of iterations of Weisfeiler-Leman identifies planar graphs, we need to find a decomposition of the graph that can be recognized by Weisfeiler-Leman, has a low height and also a small bag overlap. So this intersection between a parent and a child must be of small size. And this is necessary because the number of vertices in which we store information from components at lower levels influences the dimension of the algorithm that we need. So this is again our main theorem and a schematic view of the decomposition that we define to prove it. Again, the decomposition must have the following properties. Bags must be definable with few variables. So they must be either small, then we can have one variable for each vertex, or there must be a selection of vertices that determines the whole bag, like in this picture. Some vertices that define the whole bag. In particular, the number should not depend on the graph size. Also, the tree decomposition has a low height, or must have a low height, because each level will correspond to a constant number of iterations, and we want only asymptotically logarithmically many of them. And our decomposition must have a small adhesion, a small bag overlap between parent and child, so that the dimension can stay constant. For the first item, we will define the decomposition based on 3 connected components in the graph. Roughly speaking, every bag will be a union of at most 4 sufficiently small or 3 connected pieces. And since by Verbitsky's result we can define the 3 connected pieces with at most 3 free variables, this will yield a way to define bags with few variables, as you can see here. The following is the technical lemma which we are going to use to define a shallow tree decomposition. If we are given an arbitrary tree and select at most 3 vertices in it, there is always a tree decomposition of the tree containing those vertices that we selected in the root bag with the following properties. It has at most logarithmic height, where the height is the length of a shortest path from the root to a leaf. So here the height would be 2. It has small adhesion, so every intersection between parent and child must be small. And it has small width, which gives us a bound of 4, which is this 3 plus 1, on every bag size. And also we are guaranteed a connectedness property for such subtrees in the graphs, which is important for our induction to work. So for every node in the tree, the graph lying in the subtree rooted in this node, excluding the overlap with the parent, is connected. However, we are starting off with a general planar graph, so we don't necessarily have a tree yet. We need something to get to a tree, and for this we can use the following lemma. We can turn every connected graph into a tree with small bag overlap, small adhesion, such that each bag has a certain guaranteed structure, which we call block. So we take G, we turn it into a tree, and we are guaranteed a small adhesion and a block structure in the bags. And we then use this tree and turn it into a shallow tree via this lemma of logarithmic height, still small adhesion, and the number of blocks in each new bag is small, bounded by 4. So from the list of requirements that we had, we have the low height and we have the small adhesion. What we still need to check is this first condition, which was about the bag size, the width, because each final bag will be a union of 4 objects, 4 blocks, on the size of which we have no bound yet. Okay, so this lemma is here again, and the contents of the bags for this decomposition are these proper or degenerate blocks. What is a block and how does it guarantee us definability in our logic? Proper blocks are 3 connected. For example, this red set here is a proper block because if we remove less than 3 vertices from it, the set will stay connected via these outer paths. To see this, we can represent every outer path as a dashed red edge, and then we have a complete graph on 4 vertices, which we cannot break apart by removing vertices. And note that proper blocks have no restriction on their size. They are 3 connected, but they can be arbitrarily large. A degenerate block has size at most 3. So every block is either degenerate, which means it's small and we can just use 1 variable for each vertex in it, or it might be big, but then it is 3 connected and planar, and then Verbitsky's result gives us a method to just introduce 3 variables and obtain a formula to address every vertex separately in this block. These are our 2 technical lemmas again. We first obtain a tree in which every bag has at most 3 vertices because it's a degenerate block, or is 3 connected because it's a proper block. So each bag is definable with at most 3 variables by Verbitsky's result. And then again we obtain a tree, but this time with a logarithmic height and small bag overlap by combining at most 4 of these blocks. And the result is captured in this lengthy lemma. For every connected graph G, there is a decomposition of G of logarithmic height and small adhesion for which we have our connectedness guarantee for subtrees, and each bag is a union of at most 4 blocks or block separators for technical reasons. And since for every block, membership can be defined by fixing at most 3 variables by Verbitsky's theorem, recall this picture of the embedding that we saw, we can define membership for every bag in the final tree decomposition, because it's a union of at most 4 such blocks, with at most 4 times 3 variables. So blocks and bags are definable in C O of 1 O of log n, and skipping a long technical proof, this way we obtain a formula that guarantees us that the graph has a decomposition with the properties that we want. This is our main theorem again. What we have so far is a formula that describes the structure of the decomposition, as depicted here, but not yet the structure of the graph hidden behind the decomposition. So we have not yet gathered information about edges running within such bags, just that these bags exist, but not what's the graph structure behind it. However, by Verbitsky's result, fixing the 4 times 3 vertices in the root bag gives us a formula, or a Weisfeiler-Leman color, for each vertex in the purple bag, and therefore a formula for the isomorphism type of the purple bag. We can then address vertices separately and describe the graphs attached to them further down in the tree by induction. So we can write down a formula that says precisely that the graph attached to the vertex satisfying this particular formula and the vertex satisfying this particular formula is a union of 3 times the green isomorphism type. Recall that our lengthy lemma guaranteed us an adhesion of at most 6, so the overlap between a parent bag and a child bag is at most 6. There are at most 6 vertices that they have in common. So the proof of our main theorem proceeds over the height of the tree decomposition that we consider. We show for all heights, if G satisfies the decomposition formula from the previous slides, then there is a formula for its isomorphism type. For the inductive step, suppose we know that G satisfies the decomposition formula for height h plus 1. So G has a tree decomposition with the desired properties of height h plus 1. Then we introduce 12 variables with nested quantifiers for the 12 vertices that we fix in the root bag to canonize it or to define its isomorphism type via Verbitsky's theorem. And then the theorem also gives us a way to address every vertex in the root bag individually via its formula. So we can iterate over the possible sets of attachment vertices in the root bag by introducing 6 nested quantifiers, because the bags overlap in at most 6 vertices, and use the formulas to identify the vertices, these 6 vertices. For each of them we have a unique formula. And then we can apply the induction hypothesis, because the subtrees attached to such tuples are further down in the decomposition and they have height at most h. Altogether, we must verify that we need only a constant number of additional nested quantifiers for the induction step. To see this, we exploit the vertex identifying formulas from Verbitsky's theorem. Once we have used the formula that describes the graph attached to one such 6-element subset, we can entirely forget about the set and reuse the 6 free variables for the next 6-element subset, because we have the vertex identifying formulas anyway, so we don't have to remember them. We can just always address them with their formula when we need them. And hence the new 6 variables do not occur nested with the previous 6, and this gives us that in the induction step we only have a constant number of additional nested quantifiers. To conclude, our main theorem states that a constant dimension of the Weisfeiler-Leman algorithm suffices to identify all planar graphs in a logarithmic number of iterations. And we prove it by employing a new shallow tree decomposition that is recognized by the Weisfeiler-Leman algorithm and which enables us to use Verbitsky's result as the base case. As open questions remain, which dimension is actually needed to identify every planar graph with a logarithmic number of iterations? And is there maybe a trade-off between the dimension and the number of iterations? And finally, since planar graphs are graphs of genus 0, could this result somehow be extended to graphs only embeddable on surfaces of higher genus? What about the number of iterations on other graph classes? If you have yourself open questions or comments on this, you can contact me. Here's my email address, Thank you very much for your attention, and I hope you like this talk.